Okay, Bergson and the holographic theory of mind. Continuing series, this will be part 45A, quantum of crisis. Measuring the measurement problem. How big is it, this measurement problem of QM? Well, it's massive. Includes vagueness and completeness and nonsensical implications with locality and ontology problems mixed in, which we'll be looking at. I'm keying off what we'll call a revolt against the Copenhagen interpretation of QM, which is a la Skinner, no looking in the box. But the box is an understanding of physical reality. So the question again could be said, what is the actual basis for all the quantum weirdness, the quantum woo that leads to idealistic theories, no objective reality, and in reality, the block to looking at Bergson. So to begin, how does any crisis in quantum mechanics relate to Bergson? Easy. We're going to need a holographic physics, but not Susskind's kind, as I discussed in number 39. That is, a true model of the holographic matter field. We have to have a physics which works within the frame of Bergson's temporal metaphysic. This is a requirement for an understanding of consciousness in the brain. Bergson saw the threat to this in physics distortion, misinterpretation, and complete misuse of special relativity. He tried to ward it off, while appropriating a role to itself, that is, physics as the custodian of the theory of time. This continues unabated. In my opinion, this cancer still sits at the core of the quantum mechanics crisis. The crisis involves the nature of measurement in QM. This is equivalent to the question, what exactly is the collapse of the wave equation, Schrodinger's wave equation, when there is a measurement? The consensus has been the Copenhagen interpretation. Very succinctly, but not truly doing it justice, shut up and calculate. Don't try to understand it. In essence, the collapse is a black box, a box into which we do not look. The crisis is pretty much this. There is a growing group, but small, that is rebelling at this stricture. They say it is very important for physics to know what is happening inside the box. I've seen blogs. Things like, there is no crisis. Just a small group of dissatisfieds. QM is massively successful. Get used to what the real theory looks like. This relative to the rebellion forces. From a psychologist's perspective, I cannot resist the comparison. In essence, physics has created its own version of Skinnerian psychology, and the seeds of a very real crisis. Skinnerian psychology was a stimulus-response psychology, stimulus-response. And Skinner declared that the brain was a black box into which one could not look. To him, science is no looking inside the box. That is, no neural nets, no computer programs embodied in neural software somehow. In fact, no neural firings, apparently. This was the state of affairs. Nothing could be published with respect to the insides of the box, only the laws of reinforcement, which describe the relationship between stimulus patterns and frequencies of response, various forms of response, reinforcements to actions of the different types, reinforcement laws, until cognitive science arrived, stimulated by Chomsky and his view of language, his model of language, and Skinner was overthrown. Unfortunately, in my opinion, others stuck inside the box. But in physics, we have the box again, the measurement problem, and the collapse of the wave function, symbolized by Schrodinger's cat inside the box. And we have the Copenhagen interpretation with Niels Bohr. Science is no looking inside the box. And we have statements such as, from Bohr, there is no quantum world. There is only the abstract quantum mechanical description. We're going to meet this again. It is wrong to think that the task of physics is to find out how nature is. And this is the state of affairs in physics. Except there's some rebel forces. Again, I say again because there was reaction to this in names like Schrodinger, Einstein, and Bell, and Bohm. But now Morrison, Becker, and others. But there's another group. This group embraces the state of affairs totally. They consist of people like Castro, Henry Stapp, Kafatos, and it's just some of many. They love to make statements like, quantum mechanics is telling us there is no physical realism. There is no objective reality. The world does not exist until observed. And all QM's experimental results say this, purportedly. Of course, Mr. Rat is not quite like this. So, yes, they're defending the box and accepting measurement as a mystery explained for them by all is mind. And, as we saw in number 41, they think this solves the hard problem. Morrison would say, quote, most physicists would find themselves slightly embarrassed by this kind of openly philosophical, anti-realist speculation. But it's just a matter of degree. They're not taking the conclusions that openly that groups like Castro, Stapp, and Kafatos are. So, what really is the measurement problem? The measurement problem has several components. Here, a high-level overview, coming then a little more explanation of each. My main source in this, Travis Morrison, in this book, Foundations of Quantum Mechanics, 2017. This came from a talk, I'll put on the link in the description, by Adam Becker and his book, What is Real? When I ask who gives the decent, good explanation of the Bell's theorem, which we'll see is critical, Becker said the only true explication of Bell's theorem lies in Travis Morrison's book, hence my curiosity. So the components of the measurement problem. First, three components of the measurement problem per se, as we'll call it. A being QM's very notion of measurement is vague, undefined. B, QM's description of a system is a failure. It's incomplete. It implies two different realms. Even if measurement were precisely defined. C, it fails to provide sensible results. For example, the dead and alive cat, Schrodinger's cat in the box, a famous exposition of insensible or unsensible results, nonsensical. Secondly, the locality problem. QM must provide or must violate the relativistic C limit. That is, some interactions must be faster than light. And then three, the ontology problem. That is, there is no physical reality to the wave equation. This probably being, in my opinion, the most grievous of all. So this is the culprit, the time-dependent Schrodinger equation. Our rat notes that this is obligatory in all QM discussions. And I know for these equations, I'm just going to need you guys to pay attention to a few little things in the equations that are obvious and make nice anchors anyhow for the discussion. So here, of course, we're looking at psi. And we're talking about something how psi, that is the quantum state, evolves over time. So for a single particle of mass m moving in one dimension, so we'll have a box and a particle moving in one dimension, a line inside the box, so to speak. This becomes, voila, that expanded equation. Now we're looking at how the particle moves over time in our box. We've applied the h hat operator that is in the first equation here to get this expression, this nice complicated expression of the movement of the particle in time. So as an example of the energy eigenvalues of our particle, eigenvalues being a nice quantum mechanics term, and we can just use the term values, energy values, we'd have a little equation like this, where we have at time equals 0, we have two energy eigenvalues. You see psi 1 and psi 2 in that little equation. And that would look like this in the box. This is a superposition of the two energy states, psi 1 and psi 2. Note the constructive interference on the left. The wave forms are rising all on the left. And so this is initially where the particle is most likely to be, near the left. And now after things have evolved in time, the probability of finding that particle sloshes around a bit. So here's the new waveforms after a time t. And so now we have a little greater probability of being on the right-hand side of the box. So the typical use of this equation, given an initial state of the particle, psi at some position x, sometimes 0, solve to find the psi at some later time t. So as we've seen, it now looks like this at time t, and there's the equation for it. Later time t, and that nice complicated equation at a later time t. The Bohm rule is now a second basic postulate of the theory, and it's now introduced. It's to tell us what psi at x of t, later time t, implies about how the measurement will come out. So the probability of observing the particle at the point x is equal to the square of the wave function's modulus, or absolute value. So we see the probability of finding it at x is equal to taking the absolute value of psi x of t squared. That's the Bohm rule. So the first aspect of Bohr's rule to stress, the so-called collapse postulate. We calculate the probabilities of different measurement outcomes as follows. First, write the quantum state psi of the system we are measuring as a linear combination of eigenstates, or values, of the operator corresponding to the property, i.e. energy, momentum, we are measuring, as in our little equation there for psi. That's a sum of a set of states, ci, psi I. So linear just means psi is a sum, a big pile of these states, where that sum sign is simply saying we're adding up C1 psi 1 plus C2 psi 2, etc., until we get Cn psi n, and an n sum of states. Or just as that little equation there, we have two states, psi 1 and psi 2, that the psi is an expression of, a sum of, a pile of, or symbolized there as two curves, two waves, psi 1, psi 2, in superposition, but a linear combination. Now there's an interesting fact. If you immediately repeat a measurement, you always get the same result. That's what you'd expect. In my favorite little toaster analogy, I measure it with a ruler, and I get 9 inches. If I would measure it immediately again with the same ruler, I'd expect to get 9 inches. But Bohr's rule implies by the time the second measurement occurs, the system must be in the eigenstate, or value, for some property corresponding to the outcome of the first measurement. So I measure it there, that's where it should be, that particular curve, at that point on that curve where I have my arrow pointing. It's analogous to, shall we say, if I've measured the toaster once, but now something's changed, because what's fundamentally, to do the second measurement, well, psi starts all over again. I'm not going to get the same result. Something's happened now in terms of measurement. Now this is the collapse postulate. When a measurement occurs, and as outcome A sub n, the quantum state of the system being measured ceases to be whatever superposition it might have been previously. That is, it's going to, those multiple waves there are going to collapse to one wave. And it collapses then to the eigenstate psi of n, just one of those waves, whose eigenvalue is the realized outcome. The outcome being A sub n. The crucial point, and the reason the collapse postulate is a postulate, this is a very different sort of time evolution than wave functions normally undergo, as we've just seen, when they are evolving according to Schrodinger's equation. Coming to a screeching halt is not normal time evolution of psi, to use an example. But here's the difficulty. There is no mechanism in quantum mechanics theory to account for the breaks, other than someone looking or doing a measurement, which is a form of magic. Measuring involves a device. The device is a physical thing, such as our measuring meter with its little arm over there. It undergoes some kind of observable physical change. It is intimately coupled with the change in the state of the particle that happens at the same moment when it's measured. The measurement is a physical interaction between these two physical systems, which both change as a result. For example, suppose the particle in a box prepares so that its state is a superposition of the first few energy eigenstates, say psi 0 equals those threes, psi 1, psi 2, psi 3, and where psi 1 is the n equal 1, it is the ground state, particle in a box wave function, etc. Our plan, wait a few seconds, then measure the energy of the particle in the box. At some point, the measurement interaction occurs. The situation is now as follows. The wave function of the particle in the box has collapsed to one of the energy eigenfunctions, psi of n, with n either being 1, 2, or 3. The apparatus pointer has moved and is now pointing at the appropriate corresponding value, y, say y of n. The curious thing dynamically is that the measurement interaction seems to involve a violation of the usual dynamics for each of the interacting objects. The wave function during that brief time period collapses instead of evolving in accordance with Schrodinger's equation. And then something similar occurs with the pointer, except the pointer arm is subject to a classical law, force equals mass times acceleration, and so this motion takes time, but the collapse is instantaneous. At some point, we must come to some change in some aspect of the physical state of the apparatus for which the usual classical dynamical rules do not provide an explanation. In other words, those missing breaks. We need a theory of the breaks, a mechanism of the breaks. Otherwise, why would we need quantum mechanics at all? This brings us to the other curious thing about the whole situation. The apparatus is being described in classical terms. We do not speak, for example, of the wave function of the pointer, but instead of the pointer's position. It's the kind of thing to which we can just unproblematically attribute definite, sharp, unambiguous, unsuperposed classical properties, that is being the measuring arm. It seems to presume that quantum systems described in terms of wave functions exist in addition to classical systems. It implies two fundamentally different types of particles in the world. Those like our particle in the box that are wavy, described by psi, and those like the particles composing the pointer, which are sharp, that is, which are properly described as having indefinite positions at all times. For Morrison, all of this should make one feel very uncomfortable. There's a schizophrenic division of the world into two realms, the microscopic quantum part and the macroscopic classical part. These have completely different ontologies and completely different dynamical laws. There are apparently special dynamical rules which come into play when the two realms interact during a, quote, measurement, unquote. So we're led to this. What is the measurement process? Just what is it? What does it actually take to cause the collapse? What actually is an interaction, quote unquote, in quantum mechanics? Just observing? What causes this collapse? On this vagueness of the concept of measurement, John Bell, what exactly qualifies some physical systems to play the role of measurer? Was the wave function of the world waiting to jump for thousands of millions of years until a single living-celled creature appeared? Or did it have to wait a little longer for some better qualified system with a PhD? If the theory is to apply to anything but highly idealized laboratory operations, are we not obliged to admit that there are more or less measurement-like processes are going on more or less all the time, more or less everywhere. Do we not have quantum jumping that is collapse then all the time? So Born's role in the collapse postulate in particular seems to have been taken too literally somehow. Big macroscopic things, measuring devices, pointers, cats, trees, planets, are just large collections of electrons and other microscopic particles. If macroscopic stuff is literally made of lots and lots of little microscopic parts, then shouldn't a fully microscopic description suffice, at least in principle, even if not in practice? Shouldn't the familiar macroscopic world, large objects with definite classical properties, emerge for the more fundamental quantum mechanical description, as opposed to just being postulated? Well, there is this idea. We just use a purely microscopic part of quantum mechanics, wave functions obeying Schrodinger's equation. These describe the entire interaction between the two systems. Then everything will work out the way we want it to. The final quantum state will attribute an approximately definite position to the pointer. The wave function of the particle in a box will be one of the energy eigenstates, etc. This hope is immediately dashed from the fact that the overall Schrodinger equation is linear, as we noted. I note Sabine Hassenfelder also makes the linear critique of QM about to be made here, and I'll put that link in the description. So on this linearity, take a look at this little equation for psi, x, y, and 0, where x is the position of our particle, y is the position of the pointer, and 0 being starting at time 0. Note we're multiplying psi of the particle by y, the pointer. That is, we're bringing in the pointer into this whole system. So we have the whole system, particle and pointer. After a time t, when the measurement ceases, we have this nice, more complex equation. Note we have t now instead of 0. And we have the nice little expression on the right there for the state of y. This represents an entangled superposition of several states. In each, the particle has a definite energy. In each, the pointer's position is slightly fuzzy, but centered on a definite position corresponding to the energy of the particle. But the energy of the particle and the post-measurement position of the pointer are different in each of the superposed states. This is seriously problematic. The particle in a box does not end up in a particular energy eigenstate at all. Worse, the pointer is not localized around any particular one of what we thought previously as its possible final positions. In other words, the interaction between the particle in the box and the pointer infects the pointer with its quantum ambiguity. So in my scheme of development, we're just hit two pieces of the measurement problem per se. The measurement or the failure of quantum description, that is, there's two different realms, and Q's measurement is vague, really vague. Now the third piece, it fails to yield sensible results. Schrager presented the most famous illustration of the infection problem in the last section of his 1935 paper, quote, "The Present Situation in Quantum Mechanics." Actually, in that paper, Schrodinger illustrates the problem several times with several different examples. The cat is just the most famous. In fact, here is one before Mr. Cat, for one example. A radioactive nucleus emits an alpha particle, which causes a visible scintillation on a surrounding circular detection screen. Picture on the left there. If the alpha particle is emitted in a particular direction, the scintillation will occur at a spot on the screen in that same direction. But if both the alpha particle and the detection screen are treated quantum mechanically, again back to the same situation as treating the pointer and the particle, the pointer box and the particle together, we're treating both quantum mechanically, the linearity of Schrodinger's equation implies that if the alpha particle is emitted in a superposition of different directions, like on the right, say a spherically symmetric wave function propagating outward, the final quantum state will be an entangled superposition involving terms with scintillations, or little striking points, on all directions of the screen. That is, the microscopic quantum dynamics cannot explain how it is that the flash is seen to occur at just one particular spot on the screen. Now, Einstein and Schrodinger were corresponding. Both agreed on QM's problem. Einstein has suggested a case of a substance in unstable equilibrium, something like gunpowder. To quote him, but according to your equation, Mr. Schrodinger, after the course of a year, this is no longer the case at all. Rather, the psi function then describes a sort of a blend of not yet and of already exploded systems. Through no art of interpretation can this psi function be turned into an adequate description of a real state of affairs. For in reality, there is just no intermediary between exploded and not exploded. The dead/alive cat would follow the same illustrative principle, namely, something is wrong, very wrong, with quantum mechanics. The cat was not intended to enshrine quantum weirdness, a view virtually worshipped in popular culture, in various and sundry gurus, and in philosophy, as we've noted, such as Castro. It was intended as a reductio ad absurdum, in other words, to show the absurdity of the whole situation in quantum mechanics. So warning, the basis for the whole concept of quantum weirdness is about to be undermined in the succeeding discussion. This brings us to the ignorance interpretation of this whole situation. When we say that the wave function of the emitted alpha particle is spherically symmetric, this means that we have no idea which direction the alpha particle is going. The subjective probability distribution we would assign to its direction is spherically symmetric, but the thing itself isn't. The alpha particle itself in this view is already moving in some one particular direction. We don't know which one, but it is perfectly definite in reality all the same. Seeing a flash at some particular spot on the surrounding screen is then not a big mystery and not a proof that the microscopic quantum dynamics is wrong. It's simply the way we find out which direction the alpha particle was going all along. So the ignorance interpretation of superposition totally preempts the difficulty of Schrodinger's cat. It's amplifying fuzziness up to a macroscopic scale where it conflicts with our direct experience of the world. It provides a beautifully simple resolution of our earlier worries about the collapse postulate. If wave functions are not descriptions of the physical states of systems, but rather descriptions of the state of our knowledge of those systems, then there's nothing problematic about wave functions collapsing. It's just our lack of knowledge. But the original Bohm interpretation in 1926 was nothing but the ignorance interpretation we've discussed here. The ignorance interpretation, at least in its simplest form, cannot possibly be right. Take the double slit experiment, in the middle of which the particle's quantum state is a superposition going through slit 1 and going through slit 2. And we have our nice little equation there for psi, slit 1, slit 2. But if each particle is really just a literal particle, which has a perfectly definite, if sometimes unknown position, it is, to understate it, very difficult to understand how the subsequent particle locations could form an interference pattern. Morrison, the interference pattern strongly, indeed, I think conclusively establishes that the quantum wave function is really something physical, something real, not just a description of our incomplete state of knowledge. But a note, as we'll see, that its psi requires an infusion of ontology to truly fulfill the statement of Morrison's, and he knows this. Further, there are theorems showing that it is impossible to assign definite values to quantum properties, as taken in the framework of the ignorance interpretation. This is the famous hidden variables topic, simply this being assigning definite values to quantum properties. Example, a spin 1/2 particle, measuring each spin along the x, z, and n directions. a little picture up there, the directions where n is the plane 45 degrees between x and z, the x and z directions. Question, can there be a definite spin value along all three directions at once? Now here are the spin operators for these spin values, spin of x, spin of z, and spin of n, where spin of n is the sum of spin of x and spin of z. That is, measurement would reveal the true definite value, a value of +1 or -1 for each spin direction, a definite value which, according to the ignorance interpretation, is we're just ignorant of that definite value. It's just a matter of ignorance. Nope. Such definite values are not mathematically possible. It's mathematically impossible. A definite +1 or -1 for spin of x and spin of z gives possible values of -2, 0, and +2. That is, if we looked at spin of x and spin of z, we could see both have +1s, that would give us the +2, or both have -1s, that would give us the -2, or they could be a +1 and a -1 respectively, and that would give us the 0. So if we take the +2 outcome as an example, we'll just plug it in to the equation. Well, what we're going to see is that none of these divided by the square root of 2 gives a +1 or a -1 for the spin of n. I take the 2, for example, and plug it in. I'm going to end up with 2 over the square root of 2, or 1.414, and that's not going to equal +1 or -1. Similarly for -2 or for 0, I'm not going to get a +1 or a -1, which says that we can't get a valid spin value for the spin of n, of which we're just ignorant. This argument, it's close to von Neumann's no hidden variables proof in 1932. This proof nudged folks towards Copenhagen. We don't know what is happening, what the values are, we don't care, just calculate. But Bell would show von Neumann's proof, to quote, not merely false but foolish. Why? Because von Neumann assumed any hidden variables must obey the same mathematical relationships as their quantum mechanical operators. But this constraint makes no sense for non-commuting operators like these. These are simply non-commuting spin operators. Remember, commutative in an addition commutation, a plus b equals b plus a. That is, it doesn't matter what order. 3 plus 2 equals 2 plus 3. We add these in, we get the same result. We get 5 in this 2 plus 3 case. But that's not going to work in these spin operators, because clearly you can't. It makes a difference. You can't add, for example, sigma n and sigma z and then get sigma x. Notice it's not commutative. It's not going to work. It makes a difference what order you add those spins together. So other no hidden variable theorems have avoided this constraint, but the naive ignorance interpretation is really still not tenable. To say of all measurements that these simply reveal the values of properties that are perfectly definite, independent of the measurement procedure itself, though unknown to us, is seriously problematic. However, there does exist a perfectly viable hidden variable theory with a crucial property, namely contextuality, meaning some but not all measurements simply reveal the pre-existing values of properties. This allows it to elude all of these impossibility theorems, and this we shall see as Bohm's. So far we've seen the three components of the measurement problem per se. Vagueness, the wave equation cannot be a complete description, and nonsensical implications, with an introduction to hidden variables as already woven into the picture. Also already woven in, the locality problem to some degree. Probably everyone caught a glimmer of the inherent problem with this picture. The wave equation is expanding, or is an expanding sphere, say, of possible positions. But when the particle strikes or is measured at a spot, or do a little measurement, the entire sphere collapses instantaneously. It has to, or the particle could hit somewhere else if it waits too long. But if the wave equation expresses a physically real field, we violated the limiting speed of the causal interaction, c. We've got instantaneity. Einstein expressed this already in 1927, in this case via a hemisphere/wave passing through a slit. Einstein made other arguments, for example, the boxes. We have one particle with its wave function spread throughout the box. So we'll use the sphere again on the right-hand side for this box with its wave function, and particles with its wave function spread throughout that box. And now we split the box in two. And then we send one part to Paris and one part to Tokyo. Now we're going to measure, and we can guess the problem. We measure the wave function in Tokyo. Well, as soon as we measure, there's an instantaneous collapse in Tokyo, but also in Paris, n,000 miles away. Again, violating the principle of local causality, or the speed of light interaction limit. So in the essence, we face a dilemma between locality and completeness. If the QM wave functions provide complete descriptions of microscopic systems, then the theory must violate locality in order to make correct statistical predictions. In short, completeness implies that the collapse of the wave function is a physical dynamical process which conflicts with relativistic locality. Now, a possible out to preserve locality by denying the completeness doctrine, considering a hidden variable theory where, even when the wave function involves a superposition between the particle in the left and the right half boxes, the particle is in fact, unbeknownst to us, already in one place or the other. This again will be Bohm. Just a preview. Note the last phrase, conflicts with relativistic locality, or elsewhere array non-locality, and face the seeming daunting task of reconciling their relativity. I'm quoting from Morrison. This to me is a mass confusion, and it's ubiquitous. I have yet to see one physicist not so confused. We're talking about the limited speed of causal interaction, light. In the original framework, that is the ether, this was a rate of induction, a function of the incommensurable magnetic component and dielectric component of the ether field. This has nothing to do with measurement procedures required by two observers reciprocally at rest or in motion. That SR is, that's all it is. It's this measurement procedure between two such observers. So we're talking locality, but not relativistic locality. I've shown SR either in its consistent or inconsistent form is useless. Every physicist needs to read Bergson's duration and simultaneity like 8 times until something's understood, until they get this through. We're going to run into this and its deep implications with Bohm. The EPR paper, Einstein, Podolsky, and Rosen, 1935, is the most salient landmark in this whole discussion on hidden variables. Unfortunately, Podolsky wrote it with no Einstein review. That is, Einstein gave him the idea, and he just went and wrote it, but he never bothered to recheck with Einstein. So he obscured the essential point, the locality problem. Einstein was not happy. He used a case measuring the position and momentum of a particle. Bohr, who missed the essential point, then used this to critique the paper based on the uncertainty principle, i.e., you can't measure position and momentum in any case. But this is actually irrelevant to the EPR argument. But this helps cement in Copenhagen's framework, and we wait for Bell then nearly 30 years later. Now Bell was stimulated by Bohm's 1951 recast of EPR. Bohm's recasting. A pair of atoms in a molecule. So originally we have a molecule in which the atoms are apart, forming that molecule. Each has a spin 1/2, where each spin value is the opposite of the other, say +1 versus -1. Now the molecule dissolves. The atoms separate, moving very far apart. The spins are inherently correlated. Neither changes. Measure particle 1's spin. We automatically know particle 2's. It's the opposite. But the particles have spin on each of 3 axes, or components of spin. The wave equation only completely, precisely expresses one of these. Measuring the others, it seems one is instantly affecting the other. But we know, like the first, that all three must be correlated. Why? Because the molecule once existed and then dissolved and they separated. Hence, the wave equation is not expressing the complete reality. There are, it seems, hidden variables, or molecule, which Bohm would describe, which is to say, real causes of the correlations. Now, Bell, in one paper, noted Professor Bertelsmann's socks, who was actually a colleague of Bell's. If he wears blue, we know the other is red. We know the correlation. Why? Because Professor Bertelsmann is the cause, his mindset. The man in the street would say EPR is just the same, he said. So he reviewed Bohm's scenario with the two spin 1/2 particles. To quote, "Phenomena of this kind made physicists despair of finding any consistent space-time picture of what goes on in the atomic and subatomic scale, making a virtue of necessity and influenced by positivistic and instrumentalist philosophies. Many came to hold not only that it is difficult to find a coherent picture, but that it is wrong to look for one," referencing Copenhagen, "if not actually immoral, then certainly unprofessional." Going further still, some asserted that atomic and subatomic particles do not have any definite properties in advance of observation. This is perhaps the most standard expression of quantum weirdness, again, the Castro et al. People. Quoting Heisenberg, Bell says, "Experiments about atomic events we have to do with, phenomena that are just as real as any phenomena of daily life. But the atoms or the elementary particles are not as real. They form a world of potentialities or possibilities rather than one of things or facts." Copenhagen again. Bell going on. In Zissou Recollects, Jordan declared with emphasis that observations not only disturb what has to be measured, they produce it. In a measurement of position, for example, as performed with the gamma ray microscope, quote, "The electron is forced to a decision. We compel it to assume a definite position," quoting Zissou. "Yes, we're still seeing these claims," said Bell. "It's as if we had come to deny the reality of Bertelsmann's socks, or at least of their colors, when not looked at, and as if a child had asked, how come they always choose different colors when they are looked at? How does the second sock know what the first has done?" And, going on, EPR did not use the word paradox. They were with the man in the street in this business. For them, these correlations simply showed that the quantum theorist had been hasty in dismissing the reality of the microscopic world. In particular, Jordan had been wrong in supposing that nothing was real or fixed in that world before observation. Now notice, this is John Bell that the people like Mr. Castro, Stapp et al. Are taking issue with. Quite interesting. Thus, say in the context of measuring the particle in Japan and instantly influencing the particle in Paris, to quote, "For EPR, that would be an unthinkable, spooky action at a distance. To avoid such action at a distance, they have to attribute to the space-time regions in question real properties in advance of observation, correlated properties, like that coming from the molecule, which predetermine the outcomes of these particular observations. Since these real properties fixed in advance of observation are not contained in quantum formalism, that formalism for EPR is incomplete. It may be correct as far as it goes, but the usual quantum formalism cannot be the whole story." We shall visit the nuclear grenade Bell dropped in his theorem in Part B. How it relates to Bohm is still not understood. That is, by most people. Again, Bell supported Bohm. The actual status, nature of hidden variables we'll visit. We've been getting a sense of what these actually are. This brings us to the ontology problem. What kind of a physical thing, what ontology could the wave function possibly represent? Mathematically, psi is a function of a configuration space, an abstract mathematical space. If representing real fields like the electromagnetic field B and E, well, strange for the B, the magnetic field, and the E, the electric field, would not dwell in ordinary physical space, but rather in this abstract configuration space. Now note, the wave function uses an imaginary number, I. This is a red herring problem for its reality. Using I as just a convenience, the equation can be rewritten as two entirely real number coupled fields. So that's not the issue here on ontology. This configuration space is what worried here Schrodinger from the get-go. Lorentz, responding via letter to a copy of Schrodinger's paper, had this to say, quote, if I had to choose now between your wave mechanics and the matrix mechanics of Heisenberg, I would give the preference to the former, the wave mechanics, because of its greater intuitive clarity, so long as one only has to deal with the three coordinates, x, y, and z. If, however, there are more degrees of freedom, then I cannot interpret the waves and vibrations physically, and I must therefore decide in favor of matrix mechanics over Schrodinger. In other words, you go to 4, 5, 6, n dimensions. Lorentz can't deal with it. He doesn't know what he's visualizing anymore. He's out of the physical. You can quickly see how measurement and ontology are entwined. So we have the simple case on the left panel, the intensity of psi, of a psi function. So on the left, as my little box says, the particle starts in one energy state and evolves in space. Say Y2. But on the right side, you've got the particle starting with three energy states, three possible energy states. And we're fundamentally talking of the entanglement of the particle with the pointer here. So the high intensity region of configuration space, the gray blob, doesn't exactly look like a particle in a box in some particular state, and a pointer with some reasonably sharp location, each moving in a one-dimensional physical space. To quote Morrison here, to say quantum mechanics suffers from an ontology problem is just largely a plea for help. If you say, to quote, quantum mechanical wave function should be taken as corresponding in some sense to physical reality, as opposed, for example, to our incomplete knowledge, back to the incompleteness view, explain in concrete, mundane detail how the alleged correspondence works. Schrodinger responded to Lorentz. His original idea for physically interpreting the meaning of the wave function used the wave function to construct a mass or charge density for each particle separately, then add these together to get the total, say, charge density. This even in cases of n greater than 2 particles, where the wave function is a function of on 3 n-dimensional configuration space. So no, just 4 particles is 12 dimensions, 4 times 3, to give an idea on how abstract is this space and why Lorentz could no longer interpret things physically. So Schrodinger eventually gave up on this picture. Schrodinger's equation implies that wave packet spread, as in our little picture. As time evolves, these nice little clouds, lumps of non-zero charge density, would diffuse into an increasingly blurry haze. This doesn't correspond to the relatively sharp macroscopic world. And this sharpness, Schrodinger was at pains to capture in the fundamental theory. So Morrison looks at Schrodinger's suggestion in detail, for, as he says, something like it will be necessary, so we should try to understand the suggestion as carefully as possible. In brief, he constructs a scenario: 3 genuinely different, empirically distinguishable quantum states all produce the exact same charge distribution. That is, the physical reality of these 3 states is the same, given Schrödinger's early idea on interpretation of the wave function. So you've got 3 possible wave functions, three states. We'll take the pretend there's all 3 there, all projecting to a single charge density, d1. But this simply cannot be correct. The three states are physically different. The outcome statistics for various kinds of measurements are different for the three states. They cannot produce the same energy. He notes in mathematical terms, one loses a lot of information by projecting down the wave function into the charge density field rho. The correspondence is many to one. There are many very different wave functions, meaningfully different, physically different, that correspond to the same charge density. So, well, you'd say there must be other ideas for Morrison, but unfortunately I don't know of any other possible ideas. That is, he's out of ammo and knows of no other ammo for solving the ontology problem, translating these wave functions into something very physically real. So we have seen the measurement problem. That is the very core of QM in the problem scope, depth, gravity. At this point we have a choice. We can believe all this proves the quantum woo, or weirdness, that the world is quantum weird, that there is no objective reality. Or we can believe that what we have seen is a theoretical mess in physics that desperately needs a solution, not a dictum, e.g. no looking into that box. IMO, it has to be number 2. Anyone building a picture of the world is woo, where there is no objective reality, is building on a very shifty pile of sand. There are 3 major ways out of this. Everett's many worlds, Bohm's pilot wave, GRW. Again, I said major, there are others. We're going to look at Bohm. And did I mention Bell and his theorem? For this is critical, integral, the proper understanding of Bell with relation to Bohm. Everett has problems. Only Bohm involves an ontological solution. It is Morrison's preferred solution, and Bell's, who championed it all his life. But blocking Bohm, yes, relativity. No, it is Bohm who described the holographic theory of the material field. And as we saw, with a tantalizingly obvious modification, particularly in the theory of perception, Bohm's theory of mind comes much more into line with Bergson's holographic model. But Bohm's QM solution, the measurement solution, is virtually disregarded, and thus this vision as well of the holographic field. So next, a quantum low crisis part B, Bell, hidden variables, and Bohm. Till then, signing off.